Venus, the planet next door, and the closest thing to a twin that Earth has. In 1982, a Soviet machine stood on its surface and sent back photographs in color. Nothing has photographed that ground since. This is Cosmion. Join us as we follow the machines that reached the surface of Venus and the missions going back. For most of human history, Venus was simply the brightest thing in the sky after the Moon, and nobody had any particular reason to think it was dangerous. It is almost exactly the size of Earth. It formed from the same material in the same region of the young solar system, and through a telescope, it shows nothing but a smooth, featureless, welcoming white. Astronomers of the early 20th century looked at that unbroken cloud, reasoned that where there is cloud, there is water, and talked themselves into swamps and oceans and jungles. They were wrong by a margin that is genuinely difficult to hold in the mind. The surface of Venus is the hottest place in the solar system outside the Sun itself, and it is hotter than Mercury despite sitting nearly twice as far from the Sun, because that heat is not received so much as trapped. Carbon dioxide makes up almost the entire atmosphere, and it lies so thick and so heavy across the ground that the pressure down there at the surface is more than 90 times what you are feeling now. That is roughly what you would experience a kilometer beneath the ocean. The clouds above it are not water, but sulfuric acid, and while the wind barely stirs at ground level, the upper atmosphere races around the whole planet far faster than Venus itself can turn. The unsettling part is how Venus got that way, because the evidence increasingly suggests it was not born like this. If the young sun was fainter, as we believe it was, then Venus may well have held liquid water on its surface for a long stretch of its early history, and the two planets may have started their lives looking remarkably similar. What happened afterwards is the reason planetary scientists keep coming back. Water vapor is itself a greenhouse gas, so as Venus warmed, more of its oceans evaporated, and the thicker atmosphere trapped more heat, which evaporated more ocean again. That cycle has no natural break once it begins. The water eventually rose high enough to be broken apart by sunlight and lost to space. The carbon that would otherwise have been locked away into rock stayed in the air instead, and the planet settled into the state we find it in now. So Venus is not simply a hostile world, it is a control experiment sitting one door down from us, showing in detail what becomes of a planet almost exactly like our own, when its climate is allowed to run away from it completely. And beneath all that cloud lies a landscape nobody had ever seen, because nothing sent down there survives long enough to look around properly. Which raises the question that drives everything else in this story. If a place destroys every machine you send to it, how badly do you actually want to see the ground? The Soviet Union wanted to see it very badly indeed. Between 1961 and 1984, they sent 18 probes to Venus under the Venera program, and the early portion of that list reads as a catalogue of failure. Some missed the planet entirely, some fell silent during the cruise, and several reached the atmosphere only to be crushed on the way down, transmitting steadily until the pressure folded them. Even those failures were useful, in a grim way, because each one told the engineers exactly how deep the previous design had managed to get before it died, and each new lander was built to survive a little further down. So how do you build a machine that survives a place like that? The answer, at first, was that you did not, and you simply kept building tougher ones until one of them lasted. The breakthrough arrived on the 15th of December 1970, when the Soviet lander Venera 7 became the first spacecraft to land softly on another planet and survive long enough to say so. It was massively overbuilt. It carried almost no instruments as a result, and then an internal switchboard failed on the way down and jammed in a single position. So the only measurement the probe could send home was temperature. That should have been the end of the mission's scientific value, but it was not. Working backwards from that one stubborn number, scientists on Earth were able to calculate the pressure at the surface of Venus for the first time in history. The answer was 465 degrees and roughly 90 atmospheres. Nobody had ever measured either figure from the ground of another world, and both arrived courtesy of a machine that was, by any reasonable definition, already broken when it landed. Landing was one problem, and seeing was an entirely different one. Beneath cloud that thick, would a camera on the surface find enough light to photograph anything at all? 5 years later, on the 22nd of October 1975, the Soviet lander Venera 9 came through the cloud deck at more than 10 kilometers per second and shed its parachute at an altitude of 50 kilometers. From there, it did something no lander on any other world has ever needed to do. It simply let the enormous density of the lower atmosphere slow it down, so that it arrived at the ground traveling at roughly walking pace. The fall through the cloud layer alone took about 20 minutes. Then it opened a camera and scanned the horizon. What came back was the first photograph ever taken from the surface of another planet, and it is grey and grainy and slightly warped by the way the scanner swept back and forth across the scene. It shows a scatter of flat, broken rock running away towards a horizon that is clearly and unmistakably close, and it answered the light question immediately. The surface of Venus is not dark at all. It is dim, and it is yellow, and it goes on. Venera 10 repeated the achievement days afterwards, and 3 years later, Venera 11 and Venera 12 both landed successfully, but the imaging systems on both of them failed, and neither returned a single picture. Then, in the spring of 1982, the Soviets landed 2 machines within 4 days of each other and finally got everything they had been reaching towards since 1961. The lander of Venera 13, separated from its cruise stage on the 1st of March, fell through the acid and settled onto a plain east of a highland region called Phoebe Regio at about the speed of a dropped book. It carried cameras, a drill, a spectrometer, a seismometer, and a microphone, and it had been designed to keep working for 32 minutes. It lasted 127. In those 2 hours, it drilled into the ground, analyzed what it pulled up, identified a volcanic rock, and photographed everything around it in color. Those photographs are the reason anybody remembers the Venera program at all, and they are worth describing precisely, because they do not look the way people expect an alien world to look. The sky is a heavy sulfur yellow rather than black. The ground is a cracked pavement of flat orange slabs, tilted and stacked against each other, running out towards a horizon that seems close enough to walk to. Part of the lander itself sits in the corner of the frame, and it looks entirely ordinary, in the way a piece of farm machinery looks ordinary, which is exactly what makes the image so difficult to shake off. Venera 14 came down 4 days later, and 950 kilometers away, and it lasted 57 minutes. It also produced one of the great small tragedies of planetary exploration. The lander carried a spring-loaded arm designed to press into the ground and measure how compressible the surface was. When the camera ejected its lens cap on landing, the cap came to rest on precisely the patch of ground that the arm was about to test. It measured the lens cap. Between them, 4 Soviet landers returned images from the surface of Venus, 2 in 1975 and 2 in 1982. That is the complete list, and it has not changed in 44 years. So why did the most successful landing program in the history of planetary exploration simply stop? It was not for lack of interest, and it was not that we abandoned Venus, because orbiters have kept arriving steadily ever since. The American Magellan mission mapped almost the entire planet by radar in the early 90s, and both Europe and Japan have had spacecraft in orbit since then. Seen from above, Venus is one of the better mapped worlds in the solar system. What stopped was landing, and the reason is not mysterious so much as unforgiving. Almost everything that makes a lander work on Mars fails outright on Venus. Solar panels are close to useless beneath that permanent cloud deck. Ordinary electronics stop functioning long before anything actually melts, because silicon chips fail at temperatures far below 465 degrees, and lubricants boil, seals fail, and batteries cook well before that point too. The Venera engineers solved this by building what was effectively a thermos flask. The instrument sat inside a sealed titanium pressure sphere, chilled thoroughly before entry, and packed with material chosen to soak up heat as slowly as it possibly could, so that the electronics inside stayed survivable for as long as the shell could hold the outside world at bay. That was never cooling in any real sense, though. It was a delay. Every one of those landers was a stopwatch that started running the moment it touched the atmosphere. And when the heat finally finished crossing the shell, the mission ended in the middle of whatever it happened to be doing at the time. Venera 13 bought 2 hours, which remains the record to this day, unbroken since 1982. The calculation facing every space agency afterwards was therefore fairly bleak. A rover on Mars can work for a decade, and several of them have. A lander on Venus, built using the best method anyone has ever demonstrated, works for about as long as a football match, and costs a broadly comparable amount to build and fly. For 40 years, that arithmetic won every argument. So what finally changed the arithmetic? Not the surface, as it turned out, and not the landers either. In September 2020, a team led by the astronomer Jane Greaves announced that they had detected phosphine in the clouds of Venus. Phosphine is a simple molecule of one phosphorus atom and 3 hydrogens, and the reason its appearance mattered is that on Earth it is strongly associated with life because very little else produces it in an atmosphere full of oxygen. The quantity reported was tiny. The implication was not. What happened next is a genuinely good illustration of how science behaves when a result actually matters. Within months, separate teams reanalyzed the same observations and concluded that the signal was either an artifact of the data processing or a different molecule misidentified. The original team answered both objections in turn. A third group went back to raw measurements taken by an American probe that had flown through the clouds in 1978, reanalyzed those, and reported phosphine at concentrations higher than anyone had claimed. A long-running program using a telescope in Hawaii reported in 2024 that the detection had survived its own scrutiny. In that same year, another team published a firm upper limit and stated plainly that their observations did not support the detection at all. Both camps are still publishing, and neither has conceded. We are going to be careful here, because this is the point at which a great deal of coverage quietly stops being honest. Nobody has found life on Venus, and nobody has found convincing evidence of life on Venus. What exists is a contested measurement of a single molecule, argued over for 6 years by careful people using different instruments and arriving at different answers. But contested or not, it was enough to change something. After 4 decades in which Venus was the planet nobody could justify the cost of reaching, a question had appeared that could only be settled by going there and looking. The first answer to that question is astonishingly small. The launch company Rocket Lab, working with a team from the Massachusetts Institute of Technology, has built a probe that weighs under 1 kilogram and carries exactly one scientific instrument. It is called Venus Life Finder, and if it flies as planned, it will become the first privately funded mission ever sent to another planet. The whole thing costs under $10 million, which is worth holding against the roughly $500 million that a conventional agency mission to Venus runs to. The flight profile is close to reckless, and deliberately so. The probe enters on the night side of the planet, to keep stray sunlight out of an instrument designed to detect very faint fluorescence, and it carries no parachute whatsoever. It strikes the atmosphere at 60 times the force of gravity, falls directly into the cloud layer where the phosphine argument lives, and has roughly 210 seconds to gather its measurements before it drops below the region that matters. Everything it learns must be transmitted as it goes, on a radio channel so narrow that it carries about 12 bytes every second, which is slower than a household modem from 1980. After that, the probe keeps falling, and Venus does to it what Venus has done to everything else. The launch has been announced as no earlier than the summer of 2026. It is only fair to add that the date has already moved several times, from 2023 to early 2025 to later that year, with the schedule now tied to a new rocket becoming operational. So has it gone yet? It may already be on its way as you watch this. It may equally not fly this year at all. The second answer is the one that finally puts a camera back above that ground. The NASA mission is called Da Vinci, and it is built around a descent sphere that will enter the atmosphere and then fall for about an hour, sampling the air around it continuously the whole way down. During that fall, it will do the thing that nothing has done since 1982 and photograph the surface. The instrument that makes this possible is a camera tuned to near-infrared light, which passes through the cloud deck in a way that visible light cannot. It is aimed at a highland region called Alpha Regio, and as the sphere descends, the camera will build an increasingly detailed picture of the ground beneath it, resolving the way a photograph resolves as you walk towards it. None of this is a concept drawing. It is currently being rehearsed. Across 3 days in June 2026, the Da Vinci team flew 10 helicopter flights over a stretch of Utah desert, inside restricted United States Air Force airspace. Each flight carried a basket of 9 instruments, climbed, and then descended for around 40 minutes, across 7 different geological sites, while the camera photographed the ground below. An earlier campaign had flown drones over southwest Iceland for exactly the same reason. Why a desert and a lava field? Because they are the closest thing available on Earth to what that camera is going to see on Venus. There is something worth sitting with in that. The most recent photographs of the surface of Venus were taken by a Soviet machine in 1982, and the next ones are currently being practiced for by a helicopter flying over a desert in Utah. Da Vinci itself is real, funded and progressing, with all of its instruments through their design reviews. Its launch date is a rather different matter. 3 separate dates have been quoted publicly within the last 2 years alone. The most recent statement from the mission team actually moved it earlier rather than later, driven by what one scientist described as a rush for science now. The honest answer is the early 2030s, with the probe arriving a couple of years after launch, roughly half a century after Venera 14 stopped transmitting. The third answer is in trouble. 2 orbiters are meant to complete this return, and between them, they would give us the detailed map that a descent probe cannot. The American mission Veritas will survey the surface by radar in far finer resolution than Magellan managed a generation ago. The European mission, Envision, is designed to study the planet continuously, from its core out to its clouds, and its build contract was signed in January 2025. Neither of them is comfortable. Work on Veritas was described earlier this year as ramping up slowly, which is the language agencies tend to use when a mission is technically alive, but not really moving. Envision faces a harder problem. Its highest resolution radar instrument was to be supplied by NASA, and that contribution is now uncertain under budget pressure. The European Space Agency has begun exploring whether its member states could build the instrument themselves instead. There is very little room in the schedule to solve that. Envision has to launch by 2033, because after that the planets are simply in the wrong places, and missing the window costs at least 3 more years. So this is honestly where we stand. 3 missions are converging on the planet next door, and not one of them is secure. The first weighs less than a bag of sugar, costs less than a flat in London, has slipped its launch 3 times already, and will live for 3.5 minutes. The second is rehearsing its camera by helicopter over a desert, with a launch date that has moved 3 times in 2 years. The third may lose the instrument that justifies flying it. We are going back to Venus. We are going back if the money holds. 44 years is a very long time for a photograph to remain the most recent of anything. And yet, those 4 Soviet panoramas are still the only images ever taken from the surface of Venus. Every one of them was captured by a machine that was already dying as it worked, counting down the minutes until the heat reached its instruments. Sometime in the next decade, if the schedules hold and the funding survives, a camera will fall through those clouds again and see that ground for the first time in half a century. There is only one other world where we have ever landed something and photographed what it found beneath a thick atmosphere. It is a moon of Saturn, it has weather, and it rains there. The liquid is not water. Next time we go to Titan, subscribe, and we will take you there.